The last section in chapter 3 is called Differentials. It sort of serves as a bridge between what we've been doing and what we're going to be doing for the rest of the year. So it's kind of an important section. There's some kind of interesting stuff that we're going to do in this section, kind of confusing stuff that we're going to do in this section, but overall it boils down to the idea of differentials leading into what we're going to do next semester. So, in the last section we used tangent lines to approximate zeros. Now what we're going to do is use tangent lines to approximate functions anywhere along the function. And you say probably, what's the point? And I would agree, but there is kind of a pretty good point to it. So, using the same notation from the last section, we learned that the equation for a tangent line to any function at any point on that function is this guy right here. Y equals f at c plus f prime at c times x minus c. That's just point slope form rewritten, solved for y. And then using different notation. Instead of y1 you have f at c. Instead of x1 you have c. So that's where this point right here is coming from. C comma f of c instead of x1 comma y1. And then the slope, of course, is the derivative of the function at that x value. So that's why we write f prime of c. So we can use this idea to easily approximate the values of the function f very close to c. Because what happens is, like if I have some curve and I want to find the value of the function right there, but maybe I can't take the derivative for some reason. Well, what I can do is I can use this function right here as a good approximation of this function right here. Because what's going to happen is I'll draw that tangent line in there. That was a really bad tangent line, but you get the idea. Draw that tangent line in there, and then if I start zooming in, I start to see this guy right here, this curve, start to turn into what looks like a line. And if I zoom in close enough on that region right there, this tangent line and this function itself actually winds up being almost exactly the same. And once I get super close to it, then my approximation using the tangent line of the original function is actually going to be very accurate. So that's what we're going to do first in this section. So we need to find the tangent line approximation of that function, f of x equals 1 plus sine x, at the point 0, 1. And then use a table. So we're going to have to make a table to compare the y values of the linear function, so the tangent line that we made, compared to the original function, 1 plus sine x. So what does 1 plus sine x look like as a graph? I just want to kind of see what the graph looks like. Probably some sort of wavy feature. Where is it? It's shifted up 1. And then it has an amplitude of, so here's 1. Here's my center line. It has an amplitude of 1. It's sine, so where does it start? We would normally start at the origin, but now it's going to start here. So here's 2, here's 0. And then we're going to kind of go up, or we're going to kind of go down. We're going to go up and curve back down, and then go back up. So there's one wave. Is it pretty good? Oh, nice. I can't really tell. Yeah, that's pretty good. Okay, and we want to find the tangent line approximation to the function at the point 0, 1. Where's that? Right here. Right? Yeah. Nice. Okay, so here's my tangent line to my function, hopefully, right? I mean, that's pretty close. Can you see that as I would zoom in on this, the tangent line that I just drew in red would kind of start to mimic the graph itself as we get closer and closer to that point as I zoom in more and more and more? That's the whole point. The tangent line, as we get close to that ordered pair, will sort of coincide with the function itself to where we get a good approximation of what it is that we're looking for. So, now the question is, what do we do? If I go back to this guy right here, y equals f at c plus f prime at c times x minus c, that's the equation I'm going to be using. And I can't really remember it. So basically I'm writing the equation for my tangent line. I need the derivative. So I take the derivative of this guy and get f prime of x equals what? Cosine x. Okay, so now I can start writing my equation. I have y equals f at c. Well, c is what? 0. So f at c is what? 1. Then what? Is it minus or plus? Plus f prime at c. So now I'm looking here and I'm plugging in what? 0. So cosine 0 is 1 times x minus c is 0. So now I have my equation for my tangent line already. Simplify that down and I get y equals, there's a 1 here, this distributes in, so I just have 1 plus x. That's the equation for my tangent line. Didn't really have to do a whole lot of work there because I know that other equation now. Okay, so the next thing that we need to do is basically build a table. It says find the tangent line approximation of this function at the point 0, 1. We just did. It's right here. Then use the table to compare the y values of the linear function with those of f of x. So I want to make a table here. I'm going to need some x values. I'm going to need my f of x. And I called this y, so I'm going to call it y. F of x is the original function. Let's pick some x values that are close to 0. How about closer than negative 1? Okay, negative 0.5. Give me another value that's pretty close to 0. How about even closer than that, 0.1? So now let's mirror that on the other side, 0.1 and 0.5. We just want to see how close this approximation is actually getting. So it's going to be kind of easy to come up with the y values here, kind of. If I plug in negative 0.5 up here, what do I get? 0.5. If I plug in 0.1 up here, what do I get? Negative 0.1 up here, what do I get? .9. And then if I plug 0 in, I get, and if I plug in 0.1, I get, and if I plug in 0.5, I get. Okay. Now what is the value of the function at 0? 1. Well, it should be, right? It should be because we used that ordered pair to come up with this equation in the first place. So these should match up. But the point is, how does the function behave near to that ordered pair? That's why we're doing what we're doing here. Is our tangent line approximation a good approximation of the function itself near that ordered pair? Not at the ordered pair itself. So now we need to come up with some values here and here, which means we're going to need to use a calculator. The easiest way to do this on a calculator is to graph it and then have the table bring up your table values. Or if you want, you can just plug in these numbers into the original function a couple of times, whichever way you prefer. Oh yeah. So for f of x, plug in negative 0.5, what do we get? 0.520 some stuff. So okay, 0.521. And then how about negative 0.1? 9001. Okay. So 90016, let's make it that just so that we have something different. And then over here at 0.1. 1 point what? Okay, and then 0.5. Okay, we'll call that good. So now we want to compare these two, right? Because it says compare the y values of the linear function with those of f of x. So let's compare these. How much are we differing by here? 0.021. How much are we differing by here? 0.0002. Pretty small. And of course 0 here. How much are we differing by here? Basically that. And here? 0.21. Pretty close, yeah. And that's the point. As we get closer to the actual tangent that we made, our tangent line approximation, that's this guy, the tangent line approximation, is very close to the actual value of the function. And that is visually seen by zooming in repeatedly on your graph. You wind up with, here's the curve, or here's the tangent line, and here's the curve. They're basically exactly the same thing. So that's why you're basically exactly the same thing here. When delta x is very small, we'll talk about this in a little bit. Here's your delta x here, from 0 to negative 0.1, or from 0 to 0.1. When delta x is very small, tangent line approximation is a very good approximation of the behavior of the original function. So the important point down here at the bottom, if you choose a different point on the function, so like if it's the same problem and now I say the ordered pair 1 comma something, you have to do this process over again. You need a brand new tangent line. I mean, that should be kind of obvious, because if I'm at 1 comma something, now I'm like over here, clearly I can't use the same tangent line. As I start to get farther away, here I'm 0.5 away, and my error, I guess, is already getting kind of large compared to my error over here. So multiple points need multiple tangent lines. So when you use the tangent line to graph, when we use the tangent line to the graph at that ordered pair, we have this equation right here. That's what we just used on the last page to come up with that tangent line. This quantity right here, x minus c, is the change in x. And I just kind of mumbled that out there a couple seconds ago to throw it at you to see if it stuck. But now we need to know for sure that this guy right here is the change in x, delta x, which we've been writing as the triangle delta x. When delta x is small, we can simplify the above equation and use it as an approximation for the change in y, which we write delta y. The change in y is the change in the y coordinates, y2 minus y1. Well, this is your variable here. If I move this guy back over, then I have basically my y2 minus y1. So that's why this is turning into the delta y. So delta y winds up equaling my f prime at c, which is the derivative of the original function, times delta x from this guy right here. So this turns into delta x. The f prime at c is still there. These guys right here become the delta y. From there, we can write this in a different notation. This is not new notation, it's just a different notation that we've been using so far this year. The triangle delta x can be rewritten as dx. The f prime at c, if I want to have just a function, can be written as f prime at x. And then the triangle delta y can be rewritten as dy. And this guy right here, dy equals f prime of x dx, is your first look at a differential equation. Okay, so one use of differentials is called error propagation. How much does an error in our own measurement or whatever it is that we're doing affect the results? So like if I screw up my measurement by a little bit, how much of an effect or how much of an impact does that have on what it is that I'm doing? This is actually a fairly important thing in the field of engineering. You wouldn't want somebody who built you the airplane that you are flying in having not a very good understanding of error propagation. Why? Yeah, it doesn't do you any good if you get up there and the wing falls off. So, in our differential equation that we have, there should be an equal sign right here. That's a typo, sorry. The delta x is the measurement error, and you just need to know these things. The delta x right here is called the measurement error. The x plus delta x is the exact value. The x is the measured value, and then the delta y is the propagated error. That's like just the kind of the vocab words that go along with what it is that you're looking at in these types of problems for error propagation. So I give you a problem here as an example. The measured radius of a ball bearing is 0.7, so 7/10 of an inch. The measurement is correct to within 0.01 of an inch, so maybe you're using calipers or something like that, and they say, like stamped on the side, it says it's correct to 0.01, so 1/100th of an inch. That's pretty small. Estimate the propagated error in the volume of the ball bearing. Is this a large error or small? Find the percent error to know for sure. So we're going to calculate the propagated error, and then we're not going to know if that's a lot of error or not a lot of error. So to come up with, sort of in our own terms, something that we can kind of picture, we're going to try to calculate a percent error from that. So the first thing we want to do is kind of figure out the range that our radius can be in. The error that our radius can have. So, sorry, the radius can be between how far off? Well, I could have measured it exactly. Or I could be within plus or minus 0.01 of an inch. Okay? So that's like the window of error that I could have with my measurement. So now I'm talking about, what am I talking about? Volume of a ball, which I'm going to say is probably a sphere. So that means I can use the volume equation V equals 4/3 pi r cubed. So now I'm going to take the derivative of this guy to wind up looking like my differential equation that I just came up with. I'll wind up with dv equals, now I'm taking the derivative of this, f prime. So the 3 comes down and I'm left with 4 pi r squared. And then the change in x normally, but since we're dealing with r here, it'll be the change in r, so dr. So now all we need to do is, this is what we're looking for here. All we need to do is plug in our values. How do I know I'm looking for this? It says estimate the propagated error. The propagated error in this equation up here is the delta y, which is the dy. So I don't have y, I have v. So I'm looking for the dv here. So I have 4, I have pi, I have the radius, which is my measured value, which I have. I measured it to be 0.7 of an inch. And then the dr is the same as the dx up here. It's the measurement error. And my measurement error could be as much as plus or minus 0.01. So I just plug all that stuff in. 4 pi parentheses 0.7 squared times plus or minus 0.01. Which gives me, if I calculate all that out, I get 0. What? 0.06155, so I'll call that 8. We'll go to 5 decimal places for some reason. And that's still plus or minus, so let me do that. So that's the propagated error. What does that mean? I have no idea. But that's the propagated error. Is that large or small? I have no idea. So what we're going to do is find the percent error to know for sure. To find percent error, you find your error and divide it by the actual value that it's supposed to be. So the actual value that it's supposed to be in this case would be the actual volume of the ball if I had measured it exactly. So I'm going to take that number and divide it by the volume of the ball, which would be 4/3 pi radius to the third. You should get 0 point something, because it's a percent. Got an answer?
Yeah.
What'd you get?
0.01427.
0.0428. What's the next decimal? This is right here. 287? 285? Okay. So now to make that a percent, I move the decimal over 2 places to the right. 4.2, and I'll round to the nearest hundredth. 4.29% error. So I could be off by like as much as 4.29% with that measurement of that steel ball using that set of calipers or whatever it was that I used to measure it. Is that a big deal? It could be. It depends on what it is. If you're talking about the space shuttle, that's probably a pretty big deal. If you're talking about the door hinge on your car, probably not that big a deal. So it's all in relative to what it is that you're dealing with. But that's how you come up with an answer to a propagated error problem. All right. Here's your general formal notation for calculating differentials. Every rule that we've learned so far, product rule, quotient rule, and so on, can be written using differentials instead of what we've normally been using for derivatives. So they are here, your constant multiple rule, instead of d over dx of cu, it can be written as d of cu equals c du. Summary difference, the derivative of u plus or minus v is equal to the derivative of u plus or minus the derivative of v. Basically, that's what that says. I mean, this is nothing new. We're just writing a little bit differently. The product rule, the derivative of two things being multiplied together. We know the product rule is f prime g plus g prime f. So think of this as f g prime plus g f prime. And the same thing for the quotient rule. We know the quotient rule is f prime g minus g prime f. So think of this as your g, and this is your f prime. This is your f, this is your g prime, and then there's your f right there squared. It's nothing new, it's just a different notation. So let's do some examples. Our function y equals x squared, the derivative would be what? Good. Y prime equals 2x. The differential is going to be dy equals 2x dx. Let's do another one. What is the derivative of the next one? 2 cosine x. The differential would be dy. Yes. So what's going on here? This y prime is a shorthand way of writing dy over dx. It seems like that's what we did. It kind of seems like we multiplied both sides by dx. If you want to think of it that way, you can think of it that way. It's not really what's going on here, but that's what it winds up looking like in all circumstances. So if you want to think of it like that, go for it. How about y equals x cosine x? Y prime, that was definitely the hard part. cosine x plus, so actually minus x sine x, right? Okay, the differential would be dy equals like that. And finally, y equals 1 over x. The derivative, let me give you a hand. You guys in your quotient rule. So negative 1 over x squared. Okay, so then the differential would be negative 1 over x squared. There you go. Not that big a deal. Differentials are actually fairly straightforward. Take the derivative as you normally would, write it like that, and you're done. You can use this sort of notation for composite functions as well, which means you can use the chain rule. So do the chain rule and then do what we did. So y equals sine 3x would turn into dy equals, no, 3 cosine 3x dx. You're getting there? How about this one? dy equals okay, and then the dx. So then dy equals, we're just simplifying this, x over the square root of x squared plus 1 dx. Agreed? Okay. So that's differentials. They're not hard to work with. So the last little example of how we can use differentials, aside from how we're going to use differentials for the rest of the year, is that you can use them to approximate function values. You have a bunch of notation here. If your function is y equals f of x, then you can use this formula right here to approximate the function at some value. Use differentials, use that formula that we just have written down up there to approximate the value of the square root of 16.5. That's kind of how this is useful. So to do this, what you're going to do is you're going to let f of x equal the square root of x. The square root of some number, x. Then what you're going to say is f of x plus delta x is approximately equal to f of x plus f prime of x. That's all that it says right here. And it says a lot, but that's basically all it's saying. So now if the f of x is equal to the square root of x, then we're going to split it into this look right here. F of x plus the derivative of f of x, which winds up being 1 over 2 square root x. Then that dx. So then what you're going to do is you're going to say x equals 16. And then make delta x dx the 0.5. And once you've done that, then you can straight up substitute into that function right there. And you get the square root of 16 plus 1 over 2 square root 16 times the delta x, which is 0.5. The square root of 16 is 4 plus 1 over, the square root of 16 is 4 times 2 is 8. So 4 plus 1 over 8 times 0.5 in this case is basically 1/2. So this becomes 1/16. 4 and 1/16 is my approximation for the square root of 16.5. Which is, as a decimal, 4.0625. What is the actual square root of 16.5? 4 point something for sure. So that's my approximation. What is the square root of 16.5? 4.06202. It's a pretty close approximation.